Hey y'all, this video is going to go over graphing secant and cosecant functions, and we're going to start off with the parents of secant and cosecant, and then we're going to go into some examples doing transformations and all of that kind of stuff. So to begin with, remember secant and cosecant are actually reciprocals of functions that you already know how to graph, cosine and sine. So what we're going to do, let's actually graph secant first. It tells you what exactly to do right over here. It says step 1, we're going to graph its original. So remember, secant is a reciprocal of cosine, so we'll go ahead and graph cosine first, because this way it's going to make this process a lot easier. So let's go ahead and graph cosine. Now if you remember, cosine starts high, goes mid, low, mid, high. So if I just kind of follow that pattern, here's my cosine function. Go ahead and pause the video if you need to before I move on. And we know it continues, and I'm going to say here's my cosine function. Now to find my points and everything else that's going to go along with the actual secant function, what we're going to need to do is find where the function equals 0. Now what that means is, where does y equal 0? What are all the radians where y equals 0? So what we're going to say is, well, if you take a look at that, y equals 0 gives you all of your actual x-intercepts. So we have pi over 2, we have 3 pi over 2, and on the negative side we have negative pi over 2 and negative 3 pi over 2. Well, what happens is those are actually now the places where if we take the reciprocal of a 0, it actually becomes undefined, because the reciprocal of 0 is actually 1 over 0, which is undefined. So remember, whenever you have something undefined, you can't graph there. So it becomes an asymptote where your graph is no longer allowed to live. So this becomes an asymptote at pi over 2 because that's a 0. Same thing at 3 pi over 2. Same thing at negative pi over 2 and at negative 3 pi over 2 as well. So I've gone through and with a highlighter to mark those so I don't forget that those are there. Now all I have to do is figure out at the other angles what my values are. So let's come over here to this table. We know that we have asymptotes at pi over 2, negative pi over 2, 3 pi over 2, and negative 3 pi over 2. So let's go ahead and mark those. Instead of saying asymptote, I'm actually going to say that the value of secant at pi over 2 and at 3 pi over 2 are undefined, which is why we have asymptotes. Now that's not really the case for these other angles. So if I ask you for, before I do secant, if I ask you for cos of 0 radians, remember that's from the unit circle, at 0 radians, our coordinate is 1, 0, and our cosine then refers to our x. Our cos at 0 radians is simply 1. Now if I were to take the reciprocal of that, so if I want secant of 0, the reciprocal of 1 is also 1. So there we go. There's your first point, 0, 1 for your secant. Now let's do the same thing for pi. Now cos at pi, you can either think of the unit circle or you can look at your graph, because that also helps you out. So at pi, you have a point at negative 1. If you take the reciprocal of that, so if you want secant at pi, take the reciprocal of negative 1, it's also negative 1. Same thing for 2 pi. So if I want cos of 2 pi, that's also 1. And if I want the reciprocal of 2 pi, that is going to remain 1. So what's nice about these reciprocal functions is that these points that are here on the peaks, on the high peaks and on the low peaks, those are actually shared points, which is really nice. Now we have these points that we know, and we know that there are asymptotes. So really what these graphs are going to look like are just like that. And it's going to be repeated. So every time you have a high peak on your original, on your cos function, that's going to become an upward facing U shape, having shared that maximum point. And likewise on the bottom, all of these low points are going to become your shared point for these U-shape curves going downward. How simple. So secant is really just what I have here in red, the tops and the bottoms with the asymptotes. Now here's the thing, typically cosine, and actually sine too for that matter, the domain is always all real numbers. Now that's not going to be the case for secant, because secant, as you can see, has asymptotes. And wherever you have asymptotes, you have breaks in the domain. The domain is not continuous. So instead of listing out all of the possibilities of your asymptote locations, because it's actually continuous, it's infinite, we're going to actually just give an equation to make it simple. We're going to say the asymptotes are located at these exact places. So to write down the equation, the general form of writing this, we're going to write down the first non-negative asymptote location. The first non-negative location for your asymptote is at pi over 2. And then after pi over 2, to the right and to the left, it takes pi units to get to the next to get to the next asymptote. So because we're going to the right and to the left, I'm going to mark that by saying plus and minus pi, because that's how long it takes to get to the next one. And it's not just one time to the right and one time to the left, because like we said, there are infinite number of asymptotes that continue forever. So to represent that, we're going to say it's actually pi over 2 plus or minus pi times the constant k. And k is going to represent this infinite number of times that you have your asymptotes that repeat. So that's what you'll say for your asymptotes. Okay, so there's your secant. Now for cosecant, same idea. Remember, cosecant is a reciprocal of sine, so we're going to go ahead and graph sine first. Remember, sine starts in the middle and then it goes high and continues, so let's go ahead and put that down. So there's my sine function. Again, if you need a pause to catch up, go ahead and do that. And just like we did for secant, we're going to find all the places where the function equals 0. Now these are different locations, so just be careful. We have a 0 here at 0 radians, so there's an asymptote. We have another 0 at pi. We have another 0 at 2 pi. And on the left side we have a 0 at negative pi and at negative 2 pi. If you notice, your asymptotes are always going to be in the same location as your middle points. Remember, you have high points, you have middle points, you have low points. Your middle points are going to tell you where exactly your asymptotes should be. So just keep that in mind. It'll make it easier, even easier for you. Now all we have to do is turn your high points into upward facing U shapes, just like that. And the minimums, the low points, into U's going downward. And there you have your graph. So let's fill in the table just to be sure. At 0, I have an asymptote. It's actually undefined. Pi over 2, I have a point at 1. At pi, also undefined. At 3 pi over 2, it's negative 1. At 2 pi, again, undefined. Now if I want my asymptotes, I'm going to follow the same format. So I want my first non-negative asymptote location. My first non-negative is right over here at 0. So I'm going to say 0, and then plus or minus right and left how long it takes to get to the next asymptote, which is pi. And it's it's an infinite number of times, so we're going to say pi times k, just like we did for secant. There you go. So those are your parent functions for secant and cosecant. Now we're going to go in and do some examples of functions with transformations. So if I take a look at number 1, it's asking me to graph y equals 2 cosecant minus 1. Cosecant theta minus 1, excuse me. So what we're going to do is, to make everything a lot easier for you, I would say go ahead and actually take those transformations and graph them on the original first. So remember, cosecant is a reciprocal of sine, so go ahead and graph 2 sine theta minus 1. Notice how I've kept all the transformations the same when I'm graphing sine. Go ahead and pause the video and graph 2 sine theta minus 1. As you can see, I already have it pre-graphed here for me to make it easier and quicker. I'm going to go ahead now, and all we have to do, just like we did for the parents, is wherever we had our middle points, remember your middle points actually tell you exactly where your asymptotes are going to be. So here's a middle point, here's another middle point, there's another, that one, and that one. So those are all the places where you'll have an asymptote. So go ahead and put those in with a highlighter. Okay, notice that they did not move left or right if you compare it back to the parent function. And the reason for that is because in these transformations, we don't have a single horizontal move. No horizontal moves at all. We have our amplitude, which affects your y values, and we have a vertical slide, which also affects your y values. Vertical moves will not affect the location. They will not change the location of your asymptotes. Only horizontal moves will. Keep that in mind. Okay, so now all we have to do is flip it out just like we did on the parents. All high points become U's facing upward. And all low points become U's facing downward, just like that. And I know it's off the graph, but go ahead and show it so you know it's there. And there's your graph. So now I'm going to go back to the top and fill in all the information. Now, period, just like you know for sine and for cosine, the period is normally 2 pi. Luckily, for the reciprocals for cosecant and secant, it's the same thing. Normally, the period is 2 pi. Now remember, the only thing that changes a period is if you have a b value other than 1. In this case, and for this example, our b value is 1. So what that tells us is that the period is not affected. It is still 2 pi. We don't have a phase shift. We don't have a c value, so let's go ahead and put a slash through that, or you can write down NA. We do have a vertical slide of down 1, which you can see on the graph is right here, down 1. And our asymptotes now, again, you want to write down the first non-negative asymptote first, which is at 0. So 0 plus or minus right and left. And let's see, because it hasn't been affected, and you can actually look at the graph right now too, it only takes pi units to get to the next one. So pi times k will finish off your asymptotes for you. There you go. Now here's the thing. When you write your domain, remember, your domain is not continuous anymore because of those asymptotes. So instead of actually listing out every single interval, which is actually infinite, we're going to use the asymptote to write down the domain. So we're going to say that the domain is not where the asymptotes are. The domain is not where the asymptotes are. So we're going to say x does not equal 0 plus or minus pi k, because the asymptotes are what stop your domain. So there we go, easy enough. Now our range is going to be solely based on the actual cosecant curves, not the middle section that I did to help me. So now my range is from, let's see, bottom to top, so negative infinity to -3 hard bracket because there is a dot there. Union, because I had this huge gap right over here. This is all a gap in my cosecant function. And then it picks back up at +1 to infinity. And there's your range. There you go, first problem done. Now number 2 is a little bit more challenging because now you actually have horizontal moves. So like I said earlier, horizontal moves will affect the location of your asymptotes. So now keeping that in mind, go ahead and just like we did for the first one, go ahead and graph, instead of doing cosecant first to make it easier, keep the same transformations and go ahead and graph sine of 2 theta minus pi over 3 minus 3. Go ahead and pause the video so you can do that. You'll notice that I already have it pre-graphed for me so I can save a little bit of time. And I'm going to go ahead and just like I did for the previous example, is everywhere I have a middle point, so here, 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 those are going to be the locations of my new asymptote. So let's go ahead and put those in really quickly. And you'll notice that they are actually a lot closer than they are normally for the parent. And the reason for that is because of the move or the transformation that you have. If we look through the transformations that we do have, we have a 2 for a B value. Remember, B takes care of a horizontal stretch or shrink. And because this is a 2, we know that's a horizontal shrink. Now, if you think about that, the period is normally 2 pi, but because I have a shrink of 2, our period is going to be half of what it is normally, which is going to be pi. And so it makes sense too why these asymptotes are so close. They're actually halfway closer than they normally were. But let's continue here. It says phase shift. So we know that our phase shift is to the right, pi over 3. Vertical slide we know is down 3. And let me go ahead and finish off my graph. Remember, all the high points become high, or use pointing upward. So there we go. And all the low points become U's facing downward, just like before. Now, my asymptote locations, okay? Again, our first non-negative asymptote is, if I take a look at it, there's not one at 0. So if I go towards the right, the first one I see is at pi over 3. Plus or minus, it takes half of what it normally would take to get to the next one because we have a horizontal shrink, remember? So it actually takes 3 marks, and remember 3 marks is pi over 2. So it takes pi over 2 to get to the next one times a constant k. And our domain is going to be what our asymptotes, the domain is not going to be what the asymptotes are. So we're going to say x does not equal pi over 3 plus or minus pi over 2 times k. Our range, again, is only based on the U-shapes, not the middle sine graph. So let's see, our range is from bottom to top, so negative infinity to, that would be -4, hard bracket, union, and then it picks back up here at, let's see, that's -2 to infinity. There you go. Now secant would work the same way, and I'll do this one and I'll leave number 4 up for your practice. But number 3 is negative secant theta plus pi over 6. Now, just like we did for cosecant, go ahead and pause the video, graph y equals negative cos pi over 6 first. You'll see that I have it pre-graphed. And if I go in, now same idea. Every time I have a middle point, that's going to become an asymptote for me. So all of those places, and let me go ahead and put that in a little bit better. And just like before, all of your high points are going to become U's facing upward, and all of your low points become U's facing downward, just like that. So there's your graph. Now we just have to fill in all the information. Period is not affected because we don't have a B value, so it's still 2 pi. We have a phase shift of left pi over 6, which is 1 mark. We don't have a vertical shift, no vertical slide. And our asymptote, so again, first non-negative location for the asymptote is at pi over 3 plus or minus, and because we have no B value, we don't have a stretch or shrink, so it takes the normal amount of times or radians to get to the next asymptote, which is pi times k. So now my domain is going to be x does not equal what we just wrote down, pi over 3 plus or minus pi times k. And our range is going to be from the bottom to the top, so negative infinity to, that's at -1, hard bracket, union from 1 to infinity. And there we go. Thanks, guys.